Hi everyone, today we are going to study about one of the most interesting applications of neural style transfer, and throughout the course of the video you will be able to implement the neural style transfer algorithm along with generation of novel artistic images using the algorithm which you are going to create. So most of the algorithms you have already studied optimize a cost function. In neural style transfer algorithm, you'll optimize the cost function to get pixel values. But before we get started, I just want to show you what I created, and over left hand side is an image which I captured during my trip to hill station, and on the right is the image from which I'm going to extract the features. So it's an oil on canvas painting from Van Gogh's. It's called Starry Night, and since it's one of the most influential paintings in modern art, I decided to go with it, and this is the output which I have received from a neural net model. And I know it is not as sharp as the other images, but if I would have trained my model for more longer iterations, now the number of iterations which I used was 200. So if you would have used maybe 1000, the images which are going to be generated would be much more sharper and crisper. So it all depends upon the hardware which you are going to use and the amount of time which you are going to spend. So neural style transfer is one of the most fun techniques in deep learning, and as shown in these two images, it merges two images, namely a content image and a style image, to create a generated image. The generated image is going to be defined by G in this case, and it combines the content of the image with the style of image, which is S in this case. So there's a content image and there's a style image, and we combine these two images. We combine the features of these two images, and on the right we are going to get generated image. So let's see how we can do this. So we are going to be making use of transfer learning, and neural style transfer uses a previously trained convolutional network and builds on top of that. The idea of using a network trained on a different task and applying to it a new task is called transfer learning, which we have already learned about. And following the original paper, the authors actually used VGG19 network. It's a 19-layer version of the VGG network. This model has been already trained on a very large ImageNet database, and thus has learned to recognize a variety of low features and high level features in the deeper layers. So before we start off, we'll have to import the module. So we are going to run the following code to load parameters from the VGG model, and I'll be explaining all the underlying topics as we move forward. So this model is stored in a Python dictionary where each variable name is the key and corresponding value is a tensor containing that variable's value. To run an image through this network, you just have to feed the image to the model. And if we are using Tensorflow, we are going to be making use of this assign function like this. So this assigns the image as an input to the model. After this, if you want to access the activations of a particular layer, let's say 4.2, when a network is run on this image, you would run a TensorFlow session on the correct tensor as follows. So next we are gonna be computing the content cost. So in our example, the content image C will be the picture of the hill station, and we are going to run the code to see a picture. The content image shows the hill station's picture surrounded by scenery and nature against the mountains. So how do you ensure the generated image matches the content of the image C? So the layers of a convolutional network tend to detect low-level features such as edges and simpler textures in the shallower layers, and the later layers tend to detect high-level features such as more complex textures as well as object classes in the deeper layers. We would like the generated image to have similar content as the input image. We are going to be denoting generated image by G and the input image by C. Suppose you have chosen some layers activations to represent the content of an image. In practice, you'll get the most visually pleasing results if you choose the layer in the middle of the network. We don't have to choose any layer which is too shallow or too deep, because if we are going to be choosing the deeper layers, then the image style features of the style image are going to be more dominant over the content image, and we want a mixture of an image which has balanced features from both these images. So suppose you have picked one hidden layer to use. Now we have the image C as the input to the pre-trained VGG network. We are going to be running forward propagation, but here we have a cost function which we are going to define or denote by content cost function, and this is as shown in this picture. So here NH, NW and NC are the height, width and the number of channels of the hidden layers you have chosen and appear in normalization term in the cost. So this term over before the summation 1 by 4 times NH times NW times NC is normalization term here, and for clarity AC and AG are the volumes corresponding to a hidden layer's activations. In order to compute the cost, it might be convenient for us to unroll these volumes into a 2D matrix. So these are 3D volumes and we are going to be unrolling them into 2D matrix as shown in this picture. So we have a convolution layer. Each color represents the activation of a filter, and this on the right side is a unrolled version of this image. Each row represents the activations of a filter. So what we are going to do, we are going to be computing cost using TensorFlow. So first of all, we are going to be retrieving dimensions from G, and then we are going to retrieve dimensions from TensorX, and then we are going to unroll AC and AG as explained, and then we are going to be computing the cost, and then we are going to run our session. So we have constructed a computational graph, and then we are going to run the session. After that, we are going to compute the style cost. So this is the style image which we are going to use. This is Van Gogh Starry Night painting, and for better results, make sure that the dimensions of the content image and the style image are equal. In my case, it's 400 by 300, and if you are going to be using the two images with different dimensions, then when we are going to unroll it, Python broadcasting will not be applicable on these images and you're going to get an error. So make sure you crop the image evenly so that the dimensions of these two images match up. So next we have a style matrix. So the style matrix is also called a gram matrix. In linear algebra, the gram matrix G of a set of vectors is the matrix of dot products. In other words, G with subscript I and j compares how similar Vi is to Vj. If they are highly similar, you would then expect them to have a large value of dot product. The dot product is going to be large if the images are similar, and thus for Gij to be large, we are going to be getting know that the image is similar, and there's a style matrix is we are going to be computing style matrix by multiplying the unrolled filter matrix with the transpose. So on the left is an image NH times NW times NC and NC times, and the image which we are going to be multiplying with it is NC is a transpose of the original matrix, and then we are going to get a gram matrix. So the result is a matrix of dimension NC by NC, where NC is the number of filters. The value Gij measures how similar the activations of filter I are to the activations of filter J. One important part of the gram matrix is that the diagonal elements such as Gii also measures how active filter I is. For example, filter I is detecting vertical textures in the image. Then Gii measures how common vertical textures are in the image as a whole. If Gii is large, this means that the image has a lot of vertical textures. By capturing the prevalence of different textures of features as well as how much different features occur together, the style matrix G measures the style of an image. And using TensorFlow, we are going to implement a function that computes the gram matrix of a matrix A. And the formula is simply given by A times A transpose. So we are going to be using tf.transpose for taking out transpose, and tf.matrix multiplications, matmul, and we are going to store the value in GA. and then we are going to return it. And we are going to run the computation graph, by creating a TensorFlow session, and when we run it, we are going to get a tensor. After that, we are going to compute the style cost. So after generating the style matrix, our goal is to minimize the distance between the gram matrix of the style image S and then that of the generated image G. For now, we are now using a single hidden layer A of L, and the corresponding style cost for this layer is defined as this formula shown, where GS and G superscript G are respectively the gram matrices of the style image and the generated image. And next we are going to compute the style cost for the single layer. There are three steps to how we are going to implement this function. First of all, we are going to retrieve dimensions from hidden layer activations, and then we are going to retrieve dimensions from tensor. After that, we are going to unroll the hidden layer activations S and G into 2D matrices. After that, we are going to compute the style matrix of the image S and G, and in the end, we are going to compute the style cost. So reshape module is used to reshape the tensor which we are inputting in our function, and then we are going to be computing the loss only. And then after creating the computation graph, we are going to run it by a TensorFlow session. So now let's talk about style weights. So far you have captured the style from only one layer. We'll get better results if we merge style costs from several different layers. After completing and running the whole modules, you will be able to change how your generated image is gonna look like. So I have made this style layers. So style layers is gonna be containing what all layers I'm gonna be extracting the features from. So in this case, I'm gonna be extracting my features from convolutional layers 1, 2, 3, 4, 5. So if you are going to be fitting around all with layers, feel free to do that. I'm choosing the standardized layers, and you can combine the style costs from different layers as shown in the formula. So we are now going to compute style cost function. So it simply calls the function and several times and weights their results using the values in style layers. So we are going to be passing a Python list. Style layers is a Python list, and it contains the names of the layers we would like to extract style from, and it's going to return a tensor representing a scalar value. Style cost defined by the following equation. We are going to run a for loop, and we are going to select the output tensor of the currently selected layer. After that, S is the hidden layer activation from the layer we have selected by running the session on out, and then we are going to set G to be the hidden layer activation from some layer. Here G references model, and we'll assign the image G as the model input, so that when we run the session, we'll see the activation drawn from the appropriate layer with G as input. And then we are going to compute style cost from the current layer. We are going to add coefficient and style layer to a overall style cost, and then we are going to return it. So in the inner loop of the for loop above, G is a tensor and hasn't been evaluated yet. It will be evaluated and updated at each iteration when we run the TensorFlow graph using the model which we are going to compute later. So we are going to implement this function which we are calling it as total cost, which includes both the content cost and the style cost. So the arguments which we are going to be passing is content cost, style cost, alpha, which is a hyperparameter weighting the importance of the content cost, beta is hyperparameter weighting the importance of style cost. And then we are going to start by defining cost as J, which is alpha times content cost times beta times style cost. And then we are going to simply return it. We are going to run a TensorFlow graph to compute the whole thing. So we are going to now solve the optimization problem. So let's put everything together to implement this neural style transfer. So first of all, we are going to create an interactive session, load the content image, load the style image, randomly initialize the image to be generated. We are going to load the VGG19 model. We are going to build a TensorFlow graph. So we are going to run the content image through the VGG19 model and compute the content cost. We are going to run the style image through the VGG19 model and compute the style cost. And then we are going to compute the total cost, and then we are going to define the optimizer and the learning rate. We are going to initialize a TensorFlow graph and run it for a large number of iterations, updating the generated image at every step. So let's go through individual steps in detail. So we'll use TensorFlow to optimize with respect to G, and to do this we have to reset the graph using an interactive session. Unlike a regular session, the interactive session installs itself as a default session to build a graph. This allows you to run variables without constantly needing to refer to the session object, which simplifies the code. So we are going to let's start the interactive session. We are going to reset the graph and then we are going to start interacting session. So then after that we are going to load the shape, normalize the content image. After loading the content image, we are going to reshape and normalize it, and we are going to do the same thing with style image as well. So now we initialize the generated image as a noisy image created from the content image. By initializing the pixels of the generated image to be mostly noisy but still slightly correlated with the content image, this will help the content of the generated image more rapidly match the content of the content image. So this is how our generated image is gonna look like initially, and then we are going to load VGG19 model. To get the program to compute the content cost, C and G are appropriate hidden layer activations. We are going to use fourth convolutional layer to compute the content cost. So first of all, we are going to assign the content image to the input to the VGG19 model. Then we are going to set C to be the tensor giving the hidden layer activation, the fourth convolutional layer. Then we are going to set G to be the tensor giving the hidden layer activation for the same layer, and then we are going to compute content cost using C and G. We are going to run the session, assign the content image to be the input image of the VGG model. We are going to select the output tensor of the fourth convolutional layer. We are going to set C to be the hidden layer activation from the layer we have selected. G is the hidden activation layer from the same layer. G references fourth convolutional layer and has not been evaluated yet. We will assign the image G as the model input, and after that we are going to compute the content cost. We are going to assign the input of the image to be the style image, and then we are going to compute style cost. After that we are going to have content and style costs, and then we are going to compute total cost by calling the total cost function which we have implemented earlier. We are going to be using alpha is equal to 10 and beta is equal to 40. You may try other values of alpha and beta as well. Since these are hyperparameters, they are going to decide how our parameter is going to change. And then we are going to define optimizer. Note that we are going to use add-in optimizer in this case. You may use LBFGS also, and it may give better results. I haven't tested it yet, but LBFGS is going to consume more memory. So if you don't have any constraint regarding hardware, you may use that also. And then we are going to define our training step. We are going to implement the NN function, which initializes the variables of the TensorFlow graph. We are going to assign the input image as the input to the VGG19 model and run it. In this model, we are going to initialize global variables. So you need to run the session on the initializer, and then we are going to run noisy input image, initial generated image through the model, and then we are going to run a for loop, run a session on the train step to minimize the total cost, compute the generated image by running the session on the current model, and then we are going to print the following details after every 2 iterations, and then we are going to save current generated image in the output directory, and then we are going to save the last generated image. So you may run for loop for as long as you want. In this case we are going to be running it for 200 iterations, since I think it's a threshold from where you can start getting desired results. And if you run it for larger iterations, you may receive more sharper, crisper and better blended pictures. And then we are going to run the following cell to generate an artistic image. It should take around 3 minutes on a CPU for every 20 iterations, and you will start seeing attractive results after 140 iterations. And generally neural style transfer is done using GPUs. And that's it, you are done. After running this, you'll see that the image which has been generated is gonna be a combination of style image and the content image. And you should see something like this. Or I have more examples like this one. It's over the left side. Here's a picture of Van Gogh Starry Night, and on the right hand side is a Stanford campus picture, and you're going to see something like this. And there are many examples which you can refer to. So I hope you implement the program as we have discussed in this video, and if you have any questions or queries regarding what we have discussed so far, feel free to post them in the comment section below, or you can join the Slack channel as well. And it would be really nice to see how artistic images you come up with, and feel free to share them in the comment section below so that more people observe what ideas you come up with. Thank you for watching this video, and if you really like this video and found to be useful, please hit the like button and share them with your friends. Talk to you in next one.